A blockchain, simply put, consists of blocks and the chain which connects these blocks. The content of a block consists of a hash to the previous block, transactions, and a hash to the current block. These hashes ensure that data cannot be altered and adds an extra layer of security. What are referred to as transactions are important pieces of information that are stored inside the block. In the case of a product, let's say milk, that would be the expiration date, fat percentage, milk type, and so on. That way, all the important information is stored inside one block, and then these transactions are hashed using two 56-bit hashes, and the specific hash then is used to connect this block to other blocks, forming a chain. To ensure responsibility and accountability, the user must sign the block using a special digital signature, and the signature can then be used to validate the hash and the user. Hashes are essentially mathematical functions that turn any string of text into a random sequence of characters, such that that generated sequence of characters can identify that specific input value. Even small changes, such as changing an uppercase s into a lowercase s, should result in a noticeable change to the hash value. Importantly, these hashes are made to be nearly impossible to reverse, which ensures data immutability, as once data has entered the blockchain it cannot be altered, as then the whole chain, linked by hashes, will be broken. The private key is a randomly generated number in the range of 1 to 2 to the power of 256. The public key corresponding to the generated private key is a point on an elliptic curve which is obtained using the formula seen on screen. The parameters a and b seen in it are chosen arbitrarily and they affect the complexity of the related calculations. So, let's just put a base point g randomly on the curve, then we can draw a tangent line through the base point and somewhere this tangent line will cross the elliptic curve. Because an elliptic curve is symmetrical, we can draw a mirror point and that becomes the second g. Then we draw another line that goes through the mirror point and the base point, and then in the line crossing we draw another point and get its corresponding mirror point, which becomes 3g, and so on and so forth. That way we get many g's which we can sum up to calculate the final g value. Importantly, we cannot simply derive the private key from the formula by dividing p by g, because then it becomes the elliptic curve discrete logarithm problem and there are no known optimal ways to calculate it, especially for very large numbers. You can think of it as mixing colors. If we mix red and blue, we get purple, but if we will want to get back the same shade of red and blue that created this purple, then it would be nearly impossible. Signatures are used in combination with public keys to verify that only you could have signed this block and that the data hasn't been tampered with. A signature on a low level consists of two important values, R and S. We use the same formula that we used for our private key, but this time we generate a new random number in the range of 1 to n-1, where n is a very large prime number, so we loop through the curve and find a new point on it. The point's x-coordinate becomes the r value of the signature. Then we use the following formula, which takes z as the hashed message, p as the private key, and n as the order of the elliptic curve. For example, let's assume our p coordinates are 6 and 3, our private key is 5, random number is 3, hashed message is 9, and curve order is 17. Then we plug these values into the formula and get an s value of 14, which combined with the r of 6 yields a signature that is 6 and 14. It is worth noting that this example is a generalization and such low numbers would never be used in real blockchains. So finally, on to how a real blockchain would work. To better understand how a blockchain works, let's use an example of a supply chain. Let's assume we have a store and we want to track how coffee beans are delivered to our store. For this, we should split information into blocks. The first block, also called the Genesis block, would have a value of 0 and the transaction data would consist of farmer ID, type of coffee beans, quantity, date, and so on. The next block would be the transportation block, which would contain the transportation type, GPS route taken, container, and the temperature. The next block would be the manufacturer info block, which would store more important details about the batch itself. Then you would have the warehouse block, which would store the shipping carrier, more information about the warehouse itself, and then finally the store block, which would contain information about the store, such as the retailer ID, storage ID, shelf stock data, and others. But the blockchain doesn't have to end there, it can store any other meaningful information which depends on the requirements and the architecture. It could continue with return data, which would contain info about unsatisfied products, then warranty information if the product needs or has one, and user reviews if they were satisfied with the product and whether or not they are likely to buy more. However, in the supply chain, we may not want any random person to be able to read or write fake information into our blockchain. That is why we have permissioned blockchains, which is what sets apart the supply blockchain from a cryptocurrency blockchain, because cryptocurrency is public. Anyone has access and can add blocks to it. In the supply chain, we must be able to give permissions or grant special access to our clients or cooperation partners. Thus, we have the main administrator or organization which controls the blockchain. If we want to add partners or other organizations to our blockchain to ensure cooperation, we must issue a certificate which are tied to public keys. Permissions can be granted with smart contracts. So for example, in our small coffee bean tracking blockchain, we could grant access to different users. A farmer would have write access and could add data about his harvest in the block, but he couldn't read other data, for example transportation data. And the logistics provider could add data about conditions, but he couldn't read other data, etc. Another area where blockchains are used are in cryptocurrencies such as Bitcoin, Ethereum, Solana, and more. We are only going to discuss the Bitcoin blockchain as it uses proof of work and different cryptocurrencies to use blockchain, but it is more optimized and uses different approaches and more complex methods such as proof of stake for Ethereum. The Bitcoin blockchain works similarly to other blockchains, but rather than just validating hashes with signatures, validators or so-called miners have to find a specific predetermined hash. There are no better methods than just guessing, so it can take a long time and a lot of electricity. Once a miner finds the hash, the block is broadcasted to everyone on the blockchain network and it is added to the blockchain. For this hard work, the miner receives a reward in the form of Bitcoin. A big difference between the supply chain mentioned previously and the crypto blockchain is that crypto blockchains are fully public, which means that anyone can join, read, and add to the blockchain. But how does proof of work work? Simply put, a miner must find a specific hash that has some requirements, such as a hash that starts, for example, with 10 zeros. This is pretty easy for modern computers, as the probability to mine such a block is 0.00097%. To make things fair and balance out the mining reward process, if more miners are trying to find a block on the same network, the difficulty of finding the hash is increased by just adding more zeros in front. Let's say that for every new miner we add 5 extra zeros in front. Then for a single miner the probability decreases to a measly 0.00031%. If another miner joins, then the chances are just 1 in a billion. Blockchain is a very powerful tool which is used to store information safely. It is not widely used yet because of its complexity and lack of scalability, as well as potential legal issues. People tend to prefer less complex solutions which blockchain technology may not be able to provide. Additionally, it isn't very cheap as it requires specific setups and support for legacy systems. We hope that this video provided some insight into how this technology works and where it's applied, and thank you for watching.